Hi, I'm Mark Barsamian. In this video, we'll be discussing the end behavior of rational functions. Remember that a rational function is a ratio of polynomials, where the polynomial in the denominator is not the zero polynomial. In this video, we'll study three examples of rational functions. These three functions. In our first example, we're going to find the end behavior of this function f of x, this ugly rational function. Now remember that the phrase end behavior refers to the left end behavior and the right end behavior. That is, as x goes to negative infinity, what's the trend in the y values? And what's the trend in the y values as x goes to plus infinity? So we will investigate those two things by finding these two limits. We'll find the limit as x goes to negative infinity, and we'll find the limit as x goes to plus infinity in order to find the right end behavior. So we'll first study the limit as x goes to infinity in order to determine the right end behavior. Observe that the function f of x could be factored. So, quite a bit of work factoring that. Remember that when we found limits of the form, the limit as x approaches c of f of x, where the symbol c was a real number, we always used the factored form of the function f of x because it makes the calculation simpler. But it turns out that when finding the limit as x goes to infinity, it's the standard form that's more useful. So let's make a note of these. Standard form and factored form. The reason that the standard form is more useful is that when we're finding the limit as x goes to infinity, we are to imagine x getting more and more positive without bound. Well, when x is huge, the leading terms, these things, 7x squared in the numerator and 2x squared in the denominator, those things are gigantic. So the behavior of f of x, the behavior of this ratio of polynomials, is determined by the ratio of those leading terms. So when you find the limit as x goes to infinity, you should not even bother to factor the function. Just stick with the standard form. So the limit proceeds as follows. So the limit of f of x, that is the limit of this enormous rational function, which we use the standard form of, is equal to the limit of this simpler expression where we've kept only the leading terms. Because remember what I said a few minutes ago, when x is huge and positive, these leading terms are gigantic, and so they determine the behavior of the ratio. Now, here's another of our instances where we can cancel, but we need to explain why. X is going to infinity, so we know that x is not equal to 0. So since x is not equal to 0, we know that we can cancel x over x. So we're left with this expression, the limit as x goes to infinity of 7/2. Now, how did we get here to just writing 7/2? Well, in this limit, we're supposed to imagine x getting more and more positive without bound, and we're supposed to be considering what happens to the values of 7/2. That's this thing. But since the value of 7/2 is always the same, we realize that the limit is just simply the number 7/2. So let me say that again. This expression is telling us to imagine x getting more and more positive without bound and watch these terms to see what they're doing. Well, they're just always 7/2, and so that's why we put a 7/2 in that spot. So a sentence description of this is, as x gets more and more positive without bound, the y values get closer and closer to 7/2. So that's the sentence description. The behavior of the graph is the following. There is a horizontal asymptote on the right with line equation y equals 7/2. Now we know that that's the line equation because that number 7/2 was the value of the limit. So whatever is the number that's the value of the limit as x goes to infinity is the y value in the line equation for the horizontal asymptote on the right. Now we find the limit as x goes to negative infinity in order to determine the left-end behavior. Now this limit is going to unfold just like the previous one. So the limit turns out to be 7/2. And again, this very last step involved this kind of reasoning. So the sentence description is, as x goes to negative infinity, the y values get closer and closer to y equals 7/2. So the behavior of the graph is, this is the left end behavior. The left end of the graph has a horizontal asymptote with line equation y equals 7/2. We can confirm this result with the computer graph. Notice that there's a horizontal asymptote that has line equation y equals 7/2. That's the line equation for the horizontal asymptote. And we can see that on the right end of the graph is getting closer and closer to this asymptote. And on the left end of the graph is also getting closer and closer to this asymptote. That's the end of example 1. For example 2, we will find the limit, start over. For example 2, our question is, given this function, find these two limits and explain what those results tell us about the graph of f. Well, we start by finding the limit as x goes to infinity of g of x. If we proceed as we did in the previous example, we start with the standard form of the function. We keep only the leading terms in the next step. And then since x is going to infinity, we know that x is not equal to 0, so we can cancel, but we can only cancel the things that appear in both the numerator and the denominator. So we can cancel x squared over x squared. That leaves us with this expression, the limit of x over, the limit as x goes to infinity of the quantity 7 over 2x. Now, in this limit, we're supposed to imagine x getting more and more positive, that's this expression, without bound, and we're supposed to consider what happens to the values of 7 over 2x. Now notice that the numerator of the fraction is fixed at the value 7, while the denominator is getting huge and positive, because x is getting huge and positive, 2x is getting huge and positive. So we're dividing x by a very large positive number. So the resulting fraction will be getting closer and closer to 0. So all of this thinking that we've been doing in this extended paragraph is abbreviated in the following way. All of that stuff that I've circled in green tells us that this limit is the number 0. So all of this stuff that we wrote and discussed in this green circle is what's the thinking behind writing down a 0 there. So in the end, we have that the limit as x goes to infinity of g of x is the number 0. So the objective was to find that limit and then explain what it tells us about the behavior of the graph. Well, remember that limits as x go to infinity are telling us about the right end of the graph. What this is telling us is the following. The right end of the graph has a horizontal asymptote with line equation y equals 0. So this is the right end behavior. Now we find the limit as x goes to negative infinity of g of x. We end up with that the limit as x goes to negative infinity of g of x equals this simpler limit here. We did the same thing we've done in the last couple of problems. We started by using this standard form of the function. And then in the next step, we kept only the leading terms. In the next step, we canceled. We explained why we could cancel. Key thing was we knew that x is not equal to 0. We had to say why we knew that. And we arrived at this simpler form. Now we go through the same kind of thinking. We're supposed to imagine, according to this symbol, we're supposed to imagine x getting more and more negative, huge and negative without bound. And we're supposed to consider the values of 7 over 2x. Well, the numerator of the fraction is 7. The denominator is getting huge and negative. So the value of the fraction will be getting closer and closer to 0. So all of this green stuff, all of this green thinking goes into being able to say that this limit is the number 0. Now, what does this tell us about the behavior of the graph? Well, this tells us about the left end of the graph. The left end of the graph has a horizontal asymptote with line equation y equals 0. This is the left end behavior. So remember, the questions were to find these two limits and explain what the results tell us about the graph of G. The question was not find the end behavior. The question was just find the limits and then use the information about the limits to explain what that tells us about the graph. So we had to make the connection that when you find the limit as x goes to infinity or the limit as x goes to negative infinity, that the results tell you about the end behavior of the graph. We can confirm our results with a computer graph. Notice that in this graph, the x-axis has line equation y equals 0. And that is the horizontal asymptote on the right end of the graph, and is also the horizontal asymptote on the left end of the graph. That's the end of example 2. In example 3, we're supposed to consider this function, h of x equals this rational function. And the question is, does the graph have any horizontal asymptotes? And if so, give their line equations. So this is a different style of question. We're being asked about horizontal asymptotes. Well, the connection that we have to make is to realize that a graph having a horizontal asymptote, that phrase is actually an abbreviation for a more detailed description of the graph. So the more detailed description of a horizontal asymptote might be this sort of thing. So that would be a sentence saying that a graph has a horizontal asymptote. It would be a horizontal asymptote with line equation, y equals b. And a more detailed description of this would be, well, as x gets more and more positive without bound, the values of h of x get closer and closer to b. So that again is the description in words of what is going on with a graph if it has a horizontal asymptote. Well, realize that those words that I just wrote describing how an asymptote looks, a horizontal asymptote on the right, they have a more abbreviated description using limit notation. All of this that I've been doing is getting at this idea of what do we do with this question? We're being asked about horizontal asymptote. Well, we have made the connection that if a graph has a horizontal asymptote, then its limit is b, where b is a real number. So the question of does the graph have any horizontal asymptotes leads us to investigating the limit as x goes to infinity of h of x and seeing what we get. So in order to find out if the graph has any horizontal asymptotes, we should find the limit as x goes to infinity of h of x, and we should also find the limit as x goes to negative infinity of h of x. So let's start by finding the limit as x goes to infinity in order to determine the right end behavior. So using steps like we used in the previous couple of questions, we started by computing the limit using the standard form of the function. We kept only the leading terms to make a simpler limit expression. And then we were able to cancel x squared over x squared because we knew that x was not equal to 0. We explained why that was true. Now, finally, we arrive at this limit. Now, in this limit, we're supposed to imagine x getting more and more positive without bound, and we're supposed to consider what happens to the values of the ratio, 7x over 2. But if x is huge and positive, then 7x over 2 will also be huge and positive. That is, as x gets more and more positive without bound, the value of 7x over 2 also gets more and more positive without bound. What's a limit description of this? We'd say that the limit as x goes to infinity of 7x over 2 is infinity. So all of this stuff that I've circled here is the thinking that goes into saying that this limit is infinity. What does this tell us about the behavior of the graph? Well, the fact that the limit as x goes to infinity of h of x is infinity tells us that the right end of the graph goes up. There is no horizontal asymptote. So again, we found that the limit as x goes to infinity is infinity. That tells us the right end of the graph goes up, so there is no horizontal asymptote on the right. Next, we find the limit as x goes to negative infinity in order to determine the left end behavior. So we've arrived at this. The limit as x goes to negative infinity of h of x is equal to the limit as x goes to negative infinity of 7x over 2. So we'll take the same approach. We'll think about what we're being asked to look at in this expression. We're supposed to imagine x getting more and more negative without bound. And we're supposed to consider what happens to what happens to the values of 7x over 2. But if x is huge and negative, then 7x over 2 will also be huge and negative. That is, as x gets more and more negative without bound, the values of 7x over 2 also get more and more negative without bound. That is, the limit as x goes to negative infinity of 7x over 2 is negative infinity. So this whole paragraph is our reasoning behind putting a negative infinity for this limit. What does this tell us about the behavior of the graph? Well, since the limit as x goes to negative infinity of h of x is negative infinity, that tells us that the left end of the graph goes down. So there is no horizontal asymptote on the left either. All right, we can confirm these results with a computer graph. Here's a graph of the function h of x. Notice that there is no horizontal asymptote on either side. Now, those of you who have encountered slant asymptotes before will recognize that there is a slant asymptote, but we aren't concerned with slant asymptotes in this part of the course. We are just interested in the relationship between horizontal asymptotes and limits as x goes to infinity and limits as x goes to negative infinity. So the fact that this graph has a slant asymptote does not interest us. That's the end of example 3. Now we can generalize the results of these 3 examples. A generalization of the first example, example 1. If f is a rational function with degree of the numerator equal to the degree of the denominator, and with leading coefficients of a and b in the numerator and denominator. So that's the situation we had way up here in question A. We had degree of the numerator was 2, the degree of the denominator was 2, so the degrees were equal, and the leading coefficient in the numerator was the number 7, and the leading coefficient in the denominator was the number 2. Well, what happened in that example was the limit turned out to be 7 over 2, the ratio of those leading coefficients, and that, of course, was the height of the horizontal asymptote. So that generalizes in the following way. If we have leading coefficients a and b, then the limit as x goes to infinity of f of x is a over b, and the limit as x goes to negative infinity of f of x is also a over b. And the end behavior is the graph of f of x has a horizontal asymptote on both sides with line equation y equals a over b. That's the generalization of example 1. What about generalization of example 2? Well, in example 2, we had a function that had the degree of the numerator less than the degree of the denominator. Well, then, in that case, we found that the limit as x goes to infinity of g of x is 0, and the limit as x goes to negative infinity of g of x is 0. This generalizes to any rational function where the degree of the numerator is less than the degree of the denominator. And remember what this corresponded to. It corresponded to the graph having a horizontal asymptote on both ends with line equation y equals 0. That's the generalization of example 2. Now, what about the generalization of example 3? In example 3, we had a function h of x where the degree of the numerator was greater than the degree of the denominator. In example 3, we found that the limit as x goes to infinity of h of x was infinity. In general, we just know the following. The limit as x goes to infinity of h of x in general would either be infinity or negative infinity, and the limit as x goes to negative infinity of h of x in our example was negative infinity, but in general, for functions of this type, it would be, the limit would turn out to be plus infinity or negative infinity, depending on the function. So again, the generalization is, for some functions of this type, the limits will turn out to be infinite. Sometimes they'll turn out to be negative infinity. But they will never turn out to be 0 or to be some finite number. So what's the end behavior? Well, the end behavior is that the ends of the graph go up or down. So the right end of the graph goes up or down, and the left end of the graph goes up or down. That is to say, no horizontal asymptotes. That's the end of the video. Thank you.